Okay, we're going to be talking about light waves, diffraction, and interference. Upon successful completion of this unit, we're going to be able to describe the diffraction of light, describe the conditions needed for constructive and destructive interference, describe coherence and incoherence of light, perform calculations regarding a double slit experiment. Light is really important to us, and we have many models for light. The wave model, under many circumstances, light exhibits the same behaviors as sound or water waves, although it's a completely different type of wave. The study of light as a wave is called, of course, wave optics. The ray model, which we talked about in the previous chapters, the properties of prisms, mirrors, and lenses are best understood in terms of light rays, and of course, this is called ray optics. The photon model is a quantum idea, and light behaves like neither a wave nor a particle. Instead, light consists of photons that have both wave-like and particle-like properties, and this is the quantum theory of light. All of these models are useful, and all of them have limitations. Light can behave as any of these depending on the circumstances. If you have a water wave that's coming in, say a plane wave, plane is flat, and it hits a narrow slit, and it will spread out into this curious semicircular pattern. Actually, what's going on here is this. Here are the waves coming in, and it is encountering these edges. And light or waves will diffract. All waves can do this, will diffract around an edge. And that is they'll bend around the edge. And you can see as the edge gets narrower, causes this to get more and more curved, because look, this diffraction around this edge adds to that diffraction around that edge. And as the edges pull closer together, those two effects add to each other. And when it turns out that when the distance, the size of the slit is in about the same length as the wavelength, you end up with a maximal effect. Now, this is actually called diffraction, and all waves can exhibit this effect. But why don't we see this in light? Well, it turns out it's due to the size of the wavelength of light. Under normal circumstances, we only see sharp shadows. We don't see diffraction. We don't see fuzz around these shadows. This is what would be expected for non-interacting particles. This is what led Newton to embrace the particle model for light. But as I mentioned before, diffraction is wavelength dependent. It shows up most clearly when the size of the opening is about the same order of magnitude as the wavelength. It also helps to have waves that only have one wavelength and are in phase with each other. We need to make the opening of light the right width, preferably use monochromatic coherent light. Now, Young finally did this. He created an experiment to demonstrate the wave nature of light using two narrow, closely spaced parallel slits. Okay, now you can do this. You don't need just two slits. One slit will work. When you put laser light incident on a narrow slit, the slit is only 0.1 millimeters wide. You can barely see that with your naked eyes. It spreads out and forms an interference pattern of light and dark bands. The diffraction of light is observable if the slit width is small. This means that red light, even red light, which has the longest wavelength of all the visible light, has a very small wavelength. And you can actually see this for yourself. Now, normally I demonstrate this in front of you, but I think I can describe it well enough. Hold your hand up at arm's length so that it blocks some light, preferably like an overhead light or a desk lamp or something like that. Hold your fingers almost so that they're touching each other and look through the narrow slit between your fingers. If you look really carefully and you get this just exactly right, you're going to see a set of narrow and dark fringes, bands between your fingers. Even if you move your head from side to side, you still can see these narrow fringes. What you're seeing when you move your head from side to side, your head's over here or over here, you still see these. If this wasn't true, you would only be able to see it just when you had your head just in the right position. Okay, now shown is a modern version of Young's double slit experiment. Young used sunlight instead because sunlight's partially coherent, but now we can use laser. Lasers are monochromatic and totally coherent. We aim the laser at an opaque screen that contains these two long, narrow, closely spaced slits. Slits are each about 0.1 millimeter wide and spaced about 0.5 millimeter apart. The laser will illuminate them equally and is pointed directly at the slits and perpendicular to the screen. If light follows the ray particle model, we would just see two of these. Instead, we see this weird pattern of multiple alternating dark and light bands. The only way we can get this pattern is if this is a wave to produce a diffraction or interference pattern. Now, because light behaves as a wave, we see this pattern of light and dark bands, and you can see that between your fingers. It's kind of cool. The light from each slit will spread out. Okay, so the light from one slit will spread out, and the light from the other slit will spread out. And they will overlap. So this is the way from one slit, here's the way from the other. If they end up with crest to crest and trough to trough, you wind up with constructive interference. And you probably remember this from Physics 1 when they talked about wave interference. And this, you wind up with a bright band. So this is probably here, or it's here, or there. If instead you end up with the crest of a light from one slit meets the trough from the other, then you end up with destructive interference, and they wipe each other out. And that gives you a dark band. Now, coherence. If two light waves meet at a point or to interfere perceptibly or interfere properly, they both must have the same wavelength. The phase difference between them must remain constant with time. That is, the waves must be coherent. Laser light fills both of these things. It is coherent and monochromatic. All the waves are perfectly in step. And that's things like this. Okay, most light is incoherent. It's composed of many waves and no fixed phase difference. Sunlight is partially coherent, and Young used this in his experiment. Now, we're looking down on a double slit experiment from above. This is what the screen would look like if you were looking at it from the side here. You wind up with these bright and dark bands that are called interference fringes. If you take the line perpendicular to the screen and exactly between the two slits and take it over here, that would be a bright band, being centered on that line where it intersects the screen. And that would be the M equals 0. And that would be the 0th order number. And then if you go here further out, you would have another set of bright bands above and below the central maximum, which is what the 0th order is called. And that would be the M equals 1, or the first order. The second order would be M equals 2. Now, all of these are symmetrical around the center of the screen. The central maximum is the brightest. Others get progressively dimmer as M increases. The bright bands are called antinodes. If you remember this from vibrations, the dark bands between are nodes. Now, the phase difference between two waves can change if the waves travel past the different lengths. What appears at each point on the screen is determined by the path length difference. Delta R equals the absolute value of R2 minus R1 of the rays reaching that point. The path length difference will be delta R equals D sine theta. Now, where does this come from? Well, here's our slits, two slits, here's our screen. And each wave will bend around the corners, will interfere either constructively or destructively on the screen. And what determines what is appearing on the screen is determined by whether these waves line up. So crest meets crest and trough meets trough. You end up with constructive and a bright interference bar there. So that would be the central maximum. You can also end up where instead of being exactly in phase here, okay, now there are an integer number of wavelengths different here. You end up with a bright situation here where crest meets crest and trough meets trough. If instead the crest meets the trough, then you wind up with a destructive interference. These represents two of these rays, two of these waves. Okay, we're leaving the waves off it because it's easier to draw them like this. The screen is way off to the right here somewhere. Here's the slit 1 and slit 2. And here's the geometry of these two rays coming out to the side here. And what you're looking at here is the distance between the slits is D. The path length difference is this right here. That's the difference between this path to the screen and that path to the screen, is this little bit here, and that's associated with the sine. And it happens to be D sine theta equals the path length difference. And that will determine the number of wavelengths difference between this path and that path. Now, the bright fringe will be constructive interference, the phase difference of 0 degrees. The path length difference is an integer number of wavelengths. And this occurs when delta R equals D sine theta equals M lambda. Here's the integer number of wavelengths, where M equals 0, 1, 2. That's the order number. This tells which fringe it is. 0, 1, 2. Okay, there's one on either side. Also, if you look here, in here, okay, or in here, you can see that if this is the position of one of the fringes on the screen, the linear position of one of the fringes on the screen. Here's the distance between the slits and the screen. And you can see this angle here, and these are related to the tangent. So tangent y over L can be used to determine the fringe location in length, units of length, instead of angles. Now, dark fringes occur when there's destructive interference. That is, crest meets trough. The phase difference of 180 degrees, the path length difference of 1/2 times an odd integer number of wavelengths. So delta R equals D sine theta as before, but now it equals M plus 1/2 lambda. And where M will be 0, 1, or 2, that equals the order number. Also, we still have tangent theta equals y over L. and that can be used to find the linear difference away from the central maxima. Okay, so how does order number work? Here is a sort of a map, a chart of the intensity. Here's the central maximum right here, marked with a 0. Here are the central minimums, also marked with a 0. That's the 0th order. Here is the first maximum on either side, okay, marked with a 1. And here's the first minimum, first order minimum, and onward, 2, etc. So when m equals 0 and delta r equals 0, you have a central maxima. This is the bright band in the very center of the interference pattern. When m equals 0 and delta r is 1/2 wavelength, you end up with the first set of minima. Those are the dark fringes, 0th order dark fringes. And there'll be one on each side of the central maxima, and these occur at angles of the inverse sine of 1/2 lambda over d on either side of the central axis. There's still the 0th order because m equals 0. When m equals 1 and delta r equals lambda, you end up with the first order, which is the m equal 1 bright fringes. That's this one here and that one there. And these occur, they're called maxima. They occur at the angle of the inverse sine of lambda over d above and below the central axis. When m equals 1 and delta r is 1.5 wavelengths, then you end up with destructive interference again, and the first order set of dark fringes at theta equals the inverse sine of 1.5 lambda over d on either side of the central axis. When m equals 2 and delta r equals 2 wavelengths, right here and right here, you end up with a second order m equal 2 bright fringes, or maxima, at theta equals the inverse sine of 2 lambda over d on either side of the central axis. You can still use the tangent of theta equals y over L, where y is the distance from the center of the diffraction pattern to the fringe, and L is the distance between the slit and the viewing screen. Now, most of the time, L is much greater than y. Okay, you always put the screen pretty far away from where the slits are. So the angle will be small, less than 5 degrees. And if that's the case, unless you need something really accurate, you can use the small angle approximation. D theta then becomes approximately equal to m lambda for m equals 0, 1, 2. That's for the maxima. The minima are d theta approximately equals m plus 1/2 lambda for m equals 0, 1, 2. And theta will approximately equal y over L. We have assumed that theta equals the sine of theta equals the tangent of theta, and the small angle formula is holding, and theta has to be in radians. Remember that? So be warned, theta must be radians. Do not use this for diffraction gratings. We'll talk more about that later, or for higher orders, which will have large angles. Always check the angle. Go back and make sure it's smaller than 5 degrees. And we'll show you an example of that in a minute. Okay, the spacing, the center to center spaces, like from here to here, between the bright fringes is uniform. So in other words, this distance is the same as that distance, is the same as that one on either side. And we're going to assume the small angle approximation, and we can find that out. We're just going to use it on the central ones. So delta y will be y of the m plus 1 fringe minus y of the mth fringe. And that will be m plus 1 lambda L over d minus m lambda L over d. And if we subtract this out, we end up with lambda L over d. Lambda, of course, is the wavelength. L is the distance between the slits in the screen, and d is the slit spacing. For a pattern with n bright fringes, there must be n minus 1 spaces between them. Since the spacing is uniform, the average spacing between bright fringes must equal the overall span of the fringes divided by the number of spaces. So we can say that delta L is then delta S. Delta S is this, divided by n minus 1, where n is the number of fringes total. Now, dark fringes occur at positions where the path length difference of the waves is a half integer number of wavelengths. So delta R is the quantity m plus a half times lambda. The y position on the screen of the nth dark fringe on a screen a distance L away is, assuming the small angle approximation, y prime m equals m plus 1/2 quantity lambda L over d for m equals 0, 1, 2. These are the dark fringes where there is destructive interference. Okay, this is only for Physics 222 students and as students who have calculus. If you do not have calculus, please skip ahead to this slide number. This is number 26. Please skip ahead to that slide. Okay, now let's derive the intensity of the double slit interference pattern. From Physics 1, using a small, and we're going to use a small angle approximation on this, the net amplitude of two superimposed waves is E equals the absolute value of 2 times little e times the cosine of delta phi over 2. A little e is just the amplitude of one wave, and of course this delta phi is the phase difference between them. Now the source in this case is two slits, and the light at the two slits is in phase. So the only thing that's going to count here is the path length difference. So that's what we're going to have to calculate, and that's where this comes from. So delta phi will equal 2 pi times delta r over lambda, and that equals 2 pi times d sine theta over lambda. Now we can apply the small angle approximation to this, and that equals approximately equal to 2 pi times d tangent theta over lambda, which equals 2 pi d over lambda L times y, and that's where this comes from. Now, the intensity of a single slit with amplitude little e is just I1 equals C E squared. Of course, just remember that intensity is proportional to the amplitude squared. Or C, of course, is proportionality constant. So the double slit intensity of position Y on the screen is I double equals, you just square this and multiply by C. 4C times little e squared times cosine squared of pi d over lambda L times y. You can rewrite that for Young's interference experiment. These two waves, each with intensity I naught, will yield a resultant wave intensity I at the viewing screen with I equals 4 I naught times the cosine squared of 1/2 phi, where phi is 2 pi d over lambda times the sine of theta. Now that will result in a pattern that looks like this. Okay, now the peaks of this are 4 I naught. This is for two coherent sources. Now, if the sources were incoherent, just two lights shining on the screen, you'd wind up with this right here, 2 I naught. Of course, one light would just be this. Now, notice that instead, because these things are interfering with each other, instead of just blending together on the screen, they're actually interfering with each other. Then you wind up with this pattern. Energy is conserved. Okay, is neither created nor destroyed here. All that's been going on here is that this has rearranged itself. Instead of like this, okay, where it just fills up the entire screen like this, it arranges itself in these light and dark bands. But if you look here, this, okay, this right here is the average of this. It's kind of cool. This is not what you actually get when you do the experiment. Why? Because light's not perfect. In reality, you don't get all of this being the same amplitude as you go out across the screen here. In reality, you get something that looks like this. The central maximum is very bright, and the rest of them sort of get dimmer and dimmer as you get further and further away from the central maximum. That's because the light is not perfectly uniform. Sort of like the difference between an ideal experiment and what really happens. Okay, now combining three light waves, we're going to use phasors to combine the three light waves. Three light waves combine at a certain point where their electric field components are E1 equals E naught times the sine omega t, E2 equals E naught times the sine omega t plus 60 degrees, and E3 equals E naught times the sine omega t minus 30 degrees. We want to find the resultant component E of t at that point. The physics we're going to use is phasor analysis and vector analysis. And what the strategy is, we're going to freeze it at time t equals 0 because then we don't have to worry about the nasty omega t business. And then we're going to break this up into vertical and horizontal components using this part right here. Okay, so we write down our knowns and unknowns. E1 equals E naught times the sine omega t, and of course there'd be plus 0 degrees here in case you're curious. E2 equals E naught times the sine omega t plus 60 degrees, and E3 equals E naught times the sine omega t minus 30 degrees. We want to find out an expression for E at t, and we're going to freeze at time t equals 0 for analysis. And of course, then we draw the figure here. And we're going to break these up in the vertical and horizontal components. And of course, here's our E1 right here. And of course, this phase angle is 0, so it just lies along the horizontal axis. E2 is right here. Here's the 60-degree angle for its phase angle. That's this. Here is our E3. There's the 30-degree angle, minus 30-degree angle there. The resultant is just like you do in Physics 1. We ignore the fact that this thing's rotating, because we set time t equals 0 and we froze it at that time. So we can ignore that rotation. And of course, the result is just going to be this right here, the combination of all of them. And we're going to do this by breaking all of these up, each one of these up into vertical, horizontal components, add up all the vertical ones, add up the horizontal ones, and then do our inverse, tangent of, and then the square root of the sum of the squares. Okay, so it's just going to be sum of all of them. And of course, we're going to eventually have a thing written in the format of E equals ER. That's a resultant times the sine omega t plus beta, where ER is just the square root of the sum of the squares of the horizontal and vertical components. And beta is going to be the inverse tangent of the vertical divided by the horizontal. And of course, then this is just the sum of all of them. And the horizontal is just going to be the sum associated with the cosine. The vertical is going to be associated with the sine, just like you did in Physics 1. Okay, so then we wind up with this. E horizontal is just going to be E naught times the cosine omega t plus 0 plus the cosine omega t plus 60 plus the cosine omega t minus 30. That's the cosine part of this. E vertical is just going to be associated with the sine. And that will be E naught times the sine omega t plus 0 plus the sine omega t plus 60 degrees plus the sine omega t minus 30. We're going to freeze this at time t equals 0 so the omega t terms drop out. Then we wind up with E horizontal at time t equals 0 is E naught times the cosine of 0 degrees plus the cosine of 60 degrees plus the cosine of minus 30 degrees. If you analyze this, it ends up being 2.37 E naught. Similarly, the vertical is associated with the sine. That will be E naught times the sine of 0 degrees plus the sine of 60 degrees plus the sine of minus 30. If you analyze that, it ends up being 0.366 E naught. Now, I just repeated these on the next page for convenience. In order to find a result, we take the square root of the sum of the squares. So the square root of 2.37 E naught squared plus 0.366 E naught squared, that ends up being 2.4 E naught. That is this amplitude right here. That's that. Now for the angle, we take the inverse tangent of E vertical divided by E horizontal. So the inverse tangent of 0.366 E naught divided by 2.37 E naught. The E naughts cancel out. If they don't cancel out, you've done something wrong here. Number and E equals 8.8 degrees. That is this angle right here. There's the 8.8 degrees. So the resultant is E equals 2.4 E naught. That's the amplitude. And the sine of omega t plus 8.8 degrees, that's that angle. Okay, now we have an example of measuring the wavelength of light. This can actually be used to measure the wavelength of light. A double slit interference pattern is observed on a screen 1 meter behind two slits spaced 0.3 millimeters apart. 10 bright fringes span a distance of 1.7 centimeters. What is the wavelength of light? Well, the first thing I do is I look at these. This is very much smaller than that. So I probably can use a small angle approximation, but of course, when I get done with it, I'm going to check and make sure that's okay. The physics of this is double slit interference. We write down the knowns and unknowns, and we want to convert everything to the same units because that really makes it easy to see that probably the small angle approximation will be okay. And they want to know what is the wavelength of light. These are the number of fringes. L is much, much greater than delta y. We can simplify using the small angle approximation. And then becomes delta y equals lambda L over D, or delta y divided by n minus 1. And then we can solve this, and we wind up with lambda equal D delta y over L times n minus 1. And of course, then we have, here's our D, making sure at this point we're still in the proper units. We haven't accidentally grabbed the wrong thing. Here's our delta y. And of course, everything's in meters, so you'll be okay. It ends up being 5.7 times 10 to minus 7 meters, or 570 nanometers. And we can go back and check this and make sure it's okay. Take the inverse sine of lambda over D. If we do that, we wind up with less than 1 degree. It's about 1/10 of 1 degree. So small angle approximation would hold quite well for this, unless you were really interested in something very accurate. Okay, a laboratory experiment produces a double slit interference pattern on a screen. What is the wavelength difference between the central maximum here and this bright fringe marked with a black dot? Well, the bright fringes are all one wavelength. So this is 0, 1, 2. So this is 2 wavelengths. So it'd be 2 wavelengths. A laboratory experiment produces a double slit interference pattern on the screen. The screen is moved further away from the slits. The fringes will be further apart. Okay, delta y is proportional to L. And as you make L larger, delta y is going to get larger. A laboratory experiment produces a double slit interference pattern on a screen when using red light. If green light is used instead, with everything else the same, the bright fringes will be closer together. Green light has a smaller wavelength than red light, and delta y is proportional to wavelength. So as the wavelength gets smaller, the delta y will also get smaller. So the fringes will be closer together. And this is how you can split up light using one of these. Actually, what you do is use multiple slits, called a diffraction grating, and makes a very beautiful rainbow of light. A laboratory experiment produces a double slit interference pattern on a screen. If the slits are moved closer together, what will happen to the fringes? They will move further apart because delta y is proportional to 1 over D. Thank you very much.